All right. Good morning, ladies and gentlemen. Welcome back to probably your least favorite class right now. Just kidding. Your favorite class, yes. Okay, so I've left the exam statistics up here. I've got all the exams graded and back to you. If for some reason you didn't get your exam back, send me an email and I'll give it back to you. You should have all gotten the exam back with comments from me. Make sure you're opening your exam with like Google Chrome or Adobe Acrobat so you can see all my comments. If you sort of open it with the default, I think it's Microsoft Edge, you're not going to be able to see all the comments. So make sure you're opening it with the appropriate software to see everything. And I kind of give you a breakdown of your grade and all that sort of stuff, okay? So any questions about the exam, email me or come to office hours, we'll talk about it. General statistics here, pretty standard. Bell curve around a C. I'm happy with kind of how the exam went. I thought it was a fair exam, kind of tested not just calculation, but also some theory when it came down to like, do you know the 3D stress state for combined loading, principal stresses, failure criteria, curved beams? Hopefully there weren't any surprises there. Right. No one's really in danger of failing the class. Everyone's kind of doing well, so I wouldn't freak out too much. Okay. Couple of reminders about what we got going on. Your buckling lab is outstanding. Will be due at the beginning of the lecture period or the lab period next week, so either Tuesday or Thursday, depending on your lab. So make sure you get that done. I did have a minor update to the handout, and so there's kind of a minorly tweaked handout available on Blackboard now. Just a little bit more information on discussion question number 3, which has to do with making the graph. Hopefully it's a slightly touch bit more clear now. What I'm getting after. So make sure to take a look at that if you're still questioning how to make that graph. Otherwise, you still have a buckling homework outstanding as well, which will be due next Wednesday. So make sure you take a look at that. I think it's 4 problems. Okay, so without any further ado, if there are no questions, I'll start in on new material. And we have a new topic today. And the new topic today is going to be strain transformations. So it doesn't look like I have any questions. Okay, well then let's do the new things. Get my writing pad up here. New topic. It's a new day. Dawn of a new day. All right. Let me share my screen. Bam, writing pad. Okay, so I did post this new set of notes. So strain transformations and associated stuff. So principal strains, strain transformations, etc. So new topic here, principal strains. And strain transformations. All right. I'm going to go rather quickly through this set of notes. And that's for a couple of reasons. One, we're a little bit behind in material. It's just kind of how it is. And 2, a lot of the principal strain and strain transformation stuff is very similar to stress transformation stuff. So going through all the derivations, I don't think is all that critical. I do include the full derivations of all of these stuff in the notes if you want to dive in on that. But more or less, the strain transformation equations are going to look a lot like the stress transformation equations. The principal strain equations are going to look a lot like the principal stress equations. So more or less very redundant sort of stuff. So not going to spend a ton of time with those derivations. I'll just kind of point you to the notes for those. But I do want to spend some time talking about Hooke's law and plane stress and plane strain behavior. And I noticed on the test that the plane stress concepts were not really there from you guys. So I want to beat into your brain plane stress and plane strain concepts, so if it comes up again in the future, which it might, you'll be ready for it. All right, and I'll motivate sort of the plane stress and plane strain with Hooke's law first off. So let's do a review of Hooke's law quickly. And we'll start in 1D, and we'll work our way up from there. All right. So in 1 dimension Hooke's law, I think we're all pretty good on this, okay? So if you just had something like simple uniaxial tension, So what you kind of want to think about here is if you had a bar that looked like this, and you were loading this guy with simple, very simple loading situation. So P, or maybe you call it some axial load sigma x. All right, this is just like a one-dimensional problem where this is just like the x direction, okay? In this particular situation, like the Hooke's law is pretty simple and pretty straightforward. That's just the strain in x here is going to be equal to the stress in x divided by the modulus in the x direction, or just what we would call the modulus for an isotropic material. I think maybe there's a mistake in the notes, but I'll correct that. And then the stress in x direction is simply the modulus times strain in x. I'm going to make a note here that the notes have an error, so I'm going to have to update the notes. But here are your general like 1D Hooke's law equations. And, you know, these are the like very first equations that you probably learned in 2004, this relationship between stress and strain in one dimension. All right, that's pretty simple and straightforward. In 2D, you could have like in plane normal stresses, plus now you're talking about adding shear stresses. So in plane loads or stresses plus shear stress. And we really start talking about this in terms of like a 2D element. And this would be like the element that's on the surface of a bar. Okay, so something like your combined loading problem that you saw in your test, this is like a two-dimensional element that you really want to consider. And so your two-dimensional element that's in this certain loading situation is going to have something like sigma x, sigma y, and then obviously your shear stresses could be applied, which is like tau xy. So this is your two-dimensional sort of setup. And then the according Hooke's law here, or the Hooke's law that relate to two-dimensional, would be something like sigma x equal to elastic modulus divided by 1 minus nu squared times strain in x plus nu strain in y. That's stress in x in terms of strains. Stress in y will look similar. And then the last one. Okay, these are your two-dimensional forms of Hooke's law, writing stress in terms of strain. So stresses in terms of strains. Okay, you could also go the other way and write strains in terms of stresses, sort of by rearranging the equations. So with that, you'd have something like epsilon x is equal to 1 on the elastic modulus E, sigma x minus nu sigma y. Similar for strain in y. And also, your shear strain is just going to be your shear stress divided by the shear modulus G. So this would be strains in terms of stresses, these sort of the other way around. Okay, and this is sort of your two-dimensional Hooke's law. And here your two-dimensional state now is sort of accounting for the fact that, you know, if you pull in one direction, then there are interactions in the other direction through Poisson's ratio that sort of you have to account for, okay? And so strain in X is not just, you know, provided by axial load in X, but could also be provided by compressing the Y direction. You know, if we compress the Y direction, we're going to get strain in X, and sort of this Poisson's ratio effects. All right, so we have to be able to sort of account for that, right? Like if we have a compressive load in Y, which would be this negative value for Y, we would get some positive value for epsilon X, and we have to sort of accommodate that, and you sort of see that with these strain-stress relationships here. All right, so that's your two-dimensional Hooke's law. All of this stuff you should have seen already in 2004. The next level for Hooke's law would be 3 dimensions, and this would be sort of like the new stuff, stepping from 2004 to 3005, going from 2D to 3D. So 3D Hooke's law. The picture you want to have now in your head is this full 3-dimensional stress cube, which we've drawn many times. I'll say all 9 stresses. But really this is 6 because, you know, tau xy equals tau yx. So the picture you should have in your head, we've drawn this cube many times. And here you have your xyz. And you have all of your possible stress components. I'm not going to label all the shears here, but you get the general idea. These shear components on the surface. This here would be like tau xy. But you know that all these shears exist on this face. All right. So now the question is, what is my 3D Hooke's law relating strains to stresses or stresses to strains, depending on sort of how we want to write it. So maybe first we want to write stresses in terms of strains. Equations here are a bit long and cumbersome, but just stick with me, okay? Okay. So this is the stress in X given strains which might exist in the X, Y, or Z directions. Oh, sorry. Should be a Y. All right. How are we doing? Hand cramping up. Ooh, shake it out. Shake it, shake it, shake it, shake it, shake it. All right, so those are the normal stresses in terms of the normal strains. But we could also have shear stresses. These ones are easier, fortunately. Sorry, should be Y. All right, so those are stresses written in terms of strains. So if you know the strains, you can calculate the stresses with these equations. This would be useful if, let's say, you had a strain gauge on your piece, okay? Oh. Okay, we could also write the strains in terms of stresses. Okay, these ones are a little easier to wrap your mind around physically. All right. So here, the strain in X, 1 on the elastic modulus times sigma X minus nu sigma Y plus sigma Z. This one's pretty easy, at least for me, to sort of wrap my mind around. If I apply some stress in an X direction of a bar, then yeah, divide that by the modulus, and that's going to give me the strain in the X direction, right? If I apply some positive axial stress, that's going to give me a positive strain in the X direction, normalized by the modulus. It's sort of easy to understand. That's like your 1D Hooke's law. Then you got these other guys on the back end here, the Y and the Z direction. Okay, if I thought of like a long, slender bar, all right, and I applied like compression in Y or compression in Z, I would expect this bar to get longer in this direction by the Poisson effect. So if I have like a negative sigma Y or a negative sigma Z, I would expect a positive epsilon X, which we would get here because of this negative sign, and it's normalized by the modulus and multiplied by Poisson's ratio because of Poisson effect, okay? So it's nice to sort of like understand physically what's happening given these general equations. I'll leave this up here. Similar looking equations in the other directions. Okay. So those are axial strains written in terms of the axial stresses. But we could also have these shear strains. Those are pretty easy. That's just the shear stress normalized by the elastic modulus in all 3 of these strain states. Okay. So those are your 3-dimensional strains written in terms of the 3-dimensional stresses. Right? I'll give you a second with that if you're copying. Okay. I think this full three-dimensional Hooke's law is on kind of the common equation sheet for the class. So if you didn't, write all these down right now, you can find that on the common equation sheet for the class, or slide number 4 of my strain notes has all these equations. Okay, so why this rigmarole? Okay, well, now with this three-dimensional Hooke's law, we can maybe have a deeper discussion on what it means to be in a state of plane stress or plane strain. And that's what I want to do now, because it seems like there's a little bit of confusion on plane stress and plane strain, what it actually means, when you would have that situation, and sort of what that means for the stress state. So I saw a lot of confusion for this on the test, and I want to just make this crystal clear, okay? So I've included some additional notes here to make it crystal clear. All right, so plane stress and plane strain. All right, let's start with what we've looked at a little bit more frequently, which is plane stress. Okay, so material is in a state of plane stress if it has zero stresses on one of its three principal directions. Principal faces, principal directions, etc. Okay, so let's draw a picture of this to be sort of clear about this. All right. So let's consider like some undeformed element, two-dimensional element. Okay, let's say that this is undeformed. All right, I'll put a coordinate system here. This is the X, Z coordinate system for now. I'll make it XZ. And here I'm going to assume that the XY state is a state of plane stress. Okay, so let's consider this guy load. With stress in X, Y directions. Okay, so think of this like looking on the cube where we're loading in the X and the Y directions. Okay, so if I were to load like in the X and the Y directions, what would happen with this particular element? Well, if I'm loading in the X direction, let's make it a different color. My deformed piece is going to look like this. And that's because I'm loading here with sigma x. Also, into and out of the plane sigma y, both greater than 0. Okay, so into and out of the plane, I'm also loading. So if you sort of like rotated this 90 degrees, you would also see the same sort of situation. Okay. We would notice here, obviously, that epsilon x, the strain in x, and if we rotated this 90 degrees, epsilon y would be greater than 0. If we say that this element is in a state of plane stress, we'll say that there is no stress on the Z surface. Okay, so in that situation, sigma Z is equal to 0. Okay, so that means here that I have no stress in the Z direction. No. Okay, Nothing there. There's no stress there. Okay. However, because we have this Poisson effect, you see that there is a strain. So I'll say here that, okay, we don't have any stress in the Z, but the strain in the Z is not equal to 0. This is an important concept for plane stress, is that yes, maybe we don't have any stress in that Z direction, but if we don't have any stress in that Z direction, then the material has to sort of like squish itself in that Z direction or like compensate by Poisson effect. All right. So must deform in Z to accommodate. Stresses in X and Y. So this is a sort of a state of plane stress where this surface has no stress. Okay? So it would be a condition of sigma Z equals tau xz equals tau yz equals 0. There is no Z component of stress. That's the idea here. That's a plane stress condition. There's no stress coming off of that with that Z axis. Let's compare that to plane strain behavior. Okay. Now in plane strain behavior, one of its 3 principal axes has 0 strain, so it's different. If the strain in one principal direction is 0. So here that would be, let's assume Z direction, no strain. That would mean that we would have something like epsilon Z equals gamma x Z equals gamma y Z is 0. All of these strain components are 0. What would a picture of this look like? Okay, so again, let's sort of load in the XY direction and see what has to happen in the Z direction for this to hold. So load in XY direction and observe Z direction. All right, so let's sort of draw that. Okay, here's again our undeformed piece. Put a coordinate system on again. X, Z. Now I'm saying that I have no strain in the Z direction, okay? So what I mean by that is that whatever dimensions I had in the Z direction, when I load, I still retain those same dimensions. So now I'm loading. And it looks something like this. Here I'm still loading with like stress in the X and stress in the Y. And I'll see that, yes, I still have strain in the X and I still have strain in the Y. But now in this Z direction here, I have zero strain, meaning the dimensions in the Z are the same as they were before I loaded this. The only way that you could accomplish this is if you provide stress in the Z direction to keep that dimension from shrinking in by Poisson effect. Okay? So in this case, the stress in the Z direction must be greater than 0 to compensate for the shrinking that would occur by Poisson effect. So here, to stop epsilon Z from occurring, you need to pull with some positive sigma Z. Okay, hopefully this is kind of making sense. Usually, like when I'm in person, I bring like a piece of foam rubber to try to like demonstrate this. Okay. So what does this mean about the stress states and the strain states of these materials in principal stress, in plane stress and plane strain conditions? So let's do a comparison here of the two states. Try to split the difference here. Okay, so plane stress. This usually occurs on the surface of the material where you're free to sort of like expand and contract. Where you can expand and contract freely. Also, in thin materials. Okay, so for thin materials, it's basically all surface. Okay. So if you have some material and you're looking at, the surface of that material, and I pull on it, it will tend to shrink by Poisson effect in that sort of opposite direction. So because of that, if I pull on this and I have a plane stress condition, meaning no stress holding it or pulling it this direction, then I have to have strain occurring. So in conditions of plane stress, my out of plane strain is not 0. Okay, and that's because if I don't have any stress restricting this Poisson shrinking, then if it's shrinking freely, the strain has to be sort of like pulling this material back in. Let's compare that to plane strain. plane strain is going to occur deep within a material where it doesn't have the ability to move freely, okay? So this usually happens deep within a material in thick pieces. Where I won't use pronouns, where the material is restricted. Restricted in motion. I'll say restricted in expansion. So in this particular case, I'm pulling on a material, but to stop it from shrinking, I have to apply stress to hold it in its original zero strain condition. So in this particular situation, the out of plane stress is not zero. Okay. So we might draw that in sort of equation form. Here saying that in the plane stress condition, sigma z is equal to 0, but epsilon z is not equal to 0. In the plane strain conditions, we'd have something like epsilon z is equal to 0, no out of plane strain, but the stress in the z is not equal to 0. We have to have stress to stop the Poisson shrinking from occurring. And we can actually see this if we use the Hooke's law in 3D that we sort of wrote previously. So what actually is the strain in the z dimension if we have plane stress? So in this situation, sort of by Hooke's law, we sort of drew this before. You would have negative nu 1 minus nu epsilon x plus epsilon y. That would be your calculation of the out of plane strain components if you had plane stress. So that's going all the way back up to here. You could sort of write it in this form as well, where you're just basically making this a 0. These things are more or less equivalent. Could do a similar thing in plane strain, where since we know sigma z is not equal to 0, we could come back up to our Hooke's law where we're writing stress in terms of the strains. And we say here, okay, in plane strain, this is not equal to 0. And we could set this guy equal to 0 in plane strain. We know that to be true. And just figure out what this sigma z would be. So we just write that here directly. And it would be that sigma z is this funky E on 1 plus nu times 1 minus 2 nu. multiplied by nu times strain in X plus strain in Y. So this is the stress that you must have to stop that Poisson effect from giving you strain in the Z direction. This is required stress to stop Poisson effect from giving any component of strain in the Z. That's how you want to think about that stress. Okay, last little bit here, and then we'll finish up for today. We could talk about what the stress and the strain matrices look for each one of these situations. For plane stress. Okay, well, we know if we're in plane stress, sigma z is tau x z is tau y z is 0. And we're still going to have a situation where our gamma x z and our gamma y z are 0. But remember, epsilon z here is not 0. So what does that mean about our matrices? All right, well, my stress matrix will have components like sigma x, tau xy, sigma y, but I'll have zeros in these entries. This is what I was sort of hoping that you guys would come up with on your test, even though we kind of hadn't directly stated it. We had stated this directly before. So I was hoping that some of you would identify that point H on your structure was in a state of plane stress, and you could immediately fill a bunch of your zeros in your matrix, making your life a lot easier. But the strain matrix will look similar, except we have a strain component in Z that is not equal to 0. And that's again because when we're pulling in plane stress, we have deformation that occurs to sort of account for no stress in the third direction. All right, now plane strain behavior. This is plane strain. We know epsilon z is gamma x z, gamma y z is 0. We know here that tau x z is tau y z is 0, but sigma z is not 0. So our stress matrix, we still have in-plane components. But we do have a stress in the z direction to make sure that we're not deforming in z. in our strain matrix, we'll have strain in X, shear strain XY. And then no C if we're in plane strain. Plane strain. Here my zero occurs. Here for plane stress. Right. Those are the key differences between plane stress and plane strain. Spent the whole dang lecture on it. So now I hope it's burned in. I hope you sort of understand the differences now. And when you do your homework on strains, I'll make sure to put some questions on there that really get you thinking about the difference between plane stress and plane strain, okay? All right, that's going to be it for today. Thank you for coming. I hope you guys have a nice weekend. In-person lectures will resume next week. So if you want to come Monday, Wednesday, Friday in person, I will be there. So long for now.